admissible reference states on a single global type 3-1 factor. This band is the physical object itself, and its modular width fixes the universal quantum of action. More technically, the narrow band belongs to a type 3-1 setting and cannot be understood in type 1 terms. It reflects not a set of nearby states in the usual sense, but a structure defined by variational stability. Physical modular structure is stable only under a restricted class of admissible relational perturbations of the global state on a type 3-1 factor. These perturbations preserve coherence of modular flow, continuity of relative modular data, and the consistency of relational reconstruction. Physical reality is identified not with a single reference state, but with the entire structure defined by this admissibility condition. The minimal modular variability tolerated across admissible perturbations fixes the universal quantum of action. Algebras admit a very large space of faithful normal reference states. However, they do not admit exact tensor factorizations or localized pure vacua. As a result, an arbitrary choice of reference state does not by itself yield stable modular relations or a robust basis for emergent geometric structure. A single fixed point reference state would be highly unstable under inner automorphisms and modular co-cycle transformations in a type 3-1 setting infinitesimal Relational reparameterizations would generically displace such a state outside the physically admissible configuration. By contrast, a narrow band of admissible reference states provides a stable structure that allows modular relations to vary within controlled bounds while remaining coherent under transformations. The narrow band postulate identifies the physically relevant structure as a narrow subset of admissible reference states. This subset may be understood as a small coherence-preserving class that remains stable under the inner automorphisms and Conus co-cycle transformations implementing relational reparameterizations. Physical reality corresponds to the subset as a whole rather than its elements. From a physical perspective, the narrow band supplies a minimal but non-vanishing modular width. This width fixes a universal scale that later appears as the quantum of action and enforces coherence of modular flow. Reference states lying outside this band remain mathematically well-defined but do not support stable dynamical alignment. They therefore fail to give rise to consistent causal or geometric relations. We refer to the postulated narrow band of admissible reference states as the physical band.
The theory assumes no background space-time and no prior notion of locality.
All geometric structure arises from relations internal to the algebra. As a result, no observer, coordinate system, or reference frame is fundamental. Because space-time structure is defined relationally, physical laws cannot depend on a privileged perspective. Any admissible relational specification leads to the same structural form of emergent geometry. Modular flow associated with admissible reference states provides a notion of local time. This notion is intrinsic to the algebraic relations and does not rely on external clocks. Relative modular structure induces an ordering relation between regions. This ordering functions as a causal structure. Once space-time is reconstructed, the existence of a narrow physical band constrains how modular relations may vary, combined with the continuity and locality preserving character of type. 3-1 modular structure. These constraints exclude instantaneous propagation and imply a finite maximal speed for causal influence. Consequently, irreducible quantum behavior is present at the most fundamental level and cannot be eliminated by coarse graining. Algebras admit no exact tensor factorizations and no sharp subsystems. Relative modular phases cannot be made arbitrarily sharp. The physical band therefore carries an irreducible modular with that limits how precisely modular relations can be aligned across relational subalgebras when an effective space-time description is reconstructed. This modular limitation is encoded as a universal phase action scale, conventionally represented by Planck's constant. In this sense, Planck's reduced constant is not a dynamically derived parameter, but reflects the minimal modular dispersion compatible with stable space-time emergence within the physical band. Stable modular structure may remain mathematically well defined. Reference states in a type 3-1 setting are intrinsically global and encode holistic modular structure. Any change of the reference state corresponds to a change of the entire relational configuration rather than a localized update. Reference states varied without constraint, modular relations would generically become unstable and obstruct coherent space-time emergence. Physical admissibility, therefore, favors sharply constrained reference structures, overtaking the narrowness of the physical band. Decoherence reflects the gradual suppression of interference-sensitive relational correlations through continuous modular evolution.
It is cumulative and scale dependent, with the degree of suppression depending on the relational resolution and effective coarse graining of the description. The formulation of the theory presupposes that modular flow is well defined for admissible reference states and relational subalgebras in the physical band. This provides the basic notion of relational time required for further structure. Comparison of modular data across overlapping relational subalgebras requires the existence of relative modular operators. These operators encode how modular structure changes under shifts of relational specification. Consistency of space-time emergence requires that relative modular data satisfy co-cycle relations on overlaps. Without such coherence, no stable relational geometry can be defined. To obtain a smooth space-time, rather than a purely combinatorial structure, modular data must depend smoothly on relational labels. This smoothness underlies the emergence of differentiable structure. Additional finiteness conditions are required to prevent unbounded growth of modular information in bounded relational domains. Such conditions ensure stability of local structure. Nuclearity and split properties are natural candidates for enforcing these finiteness requirements. They restrict the effector's degrees of freedom accessible within relational subalgebras. Whether these conditions are sufficient for the reconstruction of a smooth Lorentzian spacetime in full generality remains an open mathematical problem. The present framework isolates the structures that must be analyzed. Because space-time symmetries are emergent, no other's theorem holds exactly at the modular level, but only approximately in its space-time representation. Conserved modular functionals are defined without reference to tensor factorization or local currents and are exact invariants of the modular structure. When space-time is reconstructed, these invariants appear as conserved charges and currents to the same degree of precision with which locality and Lorentz covariance emerge. Any deviation from exact conservation reflects the emergent character of space-time itself, rather than a failure of modular symmetry. Type 3-1 rigidity ensures that such deviations are extremely small within the physical band. Dimensionality of space is not assumed, but is expected to arise from the stability properties of modular relations. Spatial directions correspond to independent modular stable directions, along which quasi-local propagation and approximate locality can be maintained with Lorentzian signature. In a type 3-1 setting, the absence of minimal projections and exact factorization severely constrains how many such directions can coexist, since simply too few directions fail to support extended locality, while too many destabilize modular coherence and obstruct consistent co-cycle gluing. 3 spatial directions appear as the maximal number compatible with modular smoothness, causal ordering, and quasi-local stability within the physical band in this sense. 3-dimensional space is not imposed but selected by the modular constraints that allow space-time to emerge at all. In the modular relational framework, the equivalence principle is not postulated at the level of space-time geometry. Instead, it arises as a constraint on admissible reference states within the narrowband locally. Probabilistic relations are insensitive to global modular organization so long as coherence within the narrowband is maintained. When rendered geometrically, this insensitivity appears as the universality of free fall and local inertial behavior. Gravity is not introduced as an independent interaction, but as a manifestation of relational modular structure. Gravitational phenomena arise from how modular relations vary across overlapping relational subalgebras. Curvature in the emergent space-time reflects the local geometric effect of modular flow directions failing to align across relational overlaps. This geometric content is encoded in commutators of modular generators and in controlled variations of their relative phases. Because modular structure is state-dependent, gravitational effects are inherently tied to the reference structure within the physical band. Changes in energy content correspond to changes in modular generators rather than to external sources, acting on a background geometry. The universality of gravitational coupling follows from the universality of modular relations. All admissible relational structures contribute to modular curvature in the same way, independent of their detailed internal composition. Gravitational dynamics are expected to emerge as consistency conditions on modular structure, rather than as fundamental equations imposed a priori. Whether these conditions reproduce Einstein dynamics or a deformation thereof remains an open question. Because space-time geometry is emergent, gravity is intrinsically relational and background independent. There is no notion of gravitational interaction separate from the structure that defines space-time itself. Gravity appears weak because it arises from small misalignments of an otherwise highly rigid modular structure. In a type 3-1 setting, modular flow is largely fixed up to Connors cocycles, and relative modular phases between large or distant relational subalgebras tend to cancel as a result. Curvature generated at macroscopic scales is typically a second-order effect. Particle sectors couple to geometry only through deviations of their modular data from the background modular flow, even when local modular structure differs significantly at small scales. Only slow spatial variation of these differences contributes to emergent curvature. This mirrors the emergence of weak macroscopic responses in stiff systems whose microscopic structure is highly constrained. Gravitational self-interaction follows from the non-factorization of modular structure. Relative modular operators do not combine linearly, and modular flows associated with overlapping subalgebras are intrinsically coupled as a result. A local distortion of modular flow alters the modular relations of all overlapping regions, producing nonlinear feedback that appears in space-time as gravitational self-coupling. Because modular flow is state-dependent up to cocycles, any change in modular relations alters the effect of reference structure and feeds back into subsequent evolution. There is no clean separation between geometry and its source, and no autonomous sector corresponding to pure gravity. Gravitons are therefore not fundamental entities. Graviton-like excitations can appear only as linearized perturbations of modular flow in regimes where modular shear is small and space-time reconstruction is smooth. They are emergent, approximate quasi-particles rather than DHR sectors of the underlying algebra.
Because geometry, metric and causality are emergent rather than fundamental. Ordinary local physics probes a regime in which modular relations remain highly coherent and effectively linear. In a type 3-1 setting, relative modular operators and Connors cocycles associated with overlapping quasi-local subalgebras typically maintain stable phase alignment. In this regime, space-time has not yet become a dynamical degree of freedom, and the resulting effective description is quantum mechanical, approximately linear, and insensitive to curvature. Curvature arises only when this modular coherence is disrupted. As modular configurations are driven toward large relational shear or high effective energy density, relative modular phases cease to remain stably aligned across overlaps. Modular flow then becomes increasingly nonlinear. Quasi-local relational coherence is degraded, and the reconstruction of space-time ceases to be rigid. The resulting deformation of how causal and metric relations are glued together is what appears in the emergent space-time description as curvature.
this perspective, strong mass energy configurations do not act on a pre-existing geometry, but alter the local modular flow itself. Changes in stress energy correspond to changes in relative modular generators, which distort how effective causal cones and distances are reconstructed from relational data. This reproduces the geometric role of stress energy in general relativity without introducing gravity as an independent interaction. Conceptually, this picture parallels thermodynamic derivations of gravitational dynamics, such as Jacobson's, but replaces microscopic horizon degrees of freedom with individual relative modular phases. Gravity is therefore not fundamental, but reflects the geometry of how relational modular phase patterns either maintain coherence or lose stability within the type 3-1 relational substrate.
Local flat space-time and linear quantum dynamics are two descriptions of the same modular regime viewed through different emergent lenses. In general relativity, space-time is locally Minkowskian over sufficiently small regions. And in the absence of extreme gravitational environments, curvature effects are suppressed in physics approaches that are flat space. In MRF, an analogous statement holds at the modular level over small relational distances. And within the physical band, relative modular phases between overlapping subalgebras remain highly coherent and stably aligned. In this regime, modular flow was effectively linear. Relative modular generators commute to high precision, and modular structure does not decohere. The resulting emergent description is therefore quantum mechanical, linear, and insensitive to curvature. The relational modular framework reframes the vacuum selection problem in algebraic quantum field theory. Local operations and excitations are representation independent. MRF inherits this feature. Physical coherence and interference are encoded in modular relations between relational subalgebras rather than in the choice of a global Fock vacuum. The primary polarical quantities are relative modular phases, not vacuum expectation values. As modular phase alignment evolves and becomes unstable across increasingly large relational structures, coherence is reduced without invoking a distinguished vacuum state. In this way, questions of vacuum selection are replaced by questions about the stability of modular relations within the physical band. Spin is encoded prior to geometry through the representation theory of local modular frames. The way modular generators transform under small relabelings of relational subalgebra determines indices that become spin in the emergent description. Pre-geometric spin controls how local modular directions mix under changes of relational specification. Hypercharged pre-geometric modular invariant. In the physical band, certain co-cycle classes or conserved modular generators label admissible reference structures independently of any space-time representation. These algebraic labels are stable under admissible variations and therefore serve as primitive internal charges. Universality of hypercharge assignments is explained by their origin as global modular invariants, because these invariants live at the level of the global algebra. Their action on all admissible relational structures is uniform. This provides a structural account of universal charge couplings. Electric charge is a derived notion that requires emergent gauge structure and locality. The combination of pre-geometric invariants with local gauge generators in the reconstructed spacetime produces the observable electric charge. Thus, observed charge spectra are tests of how modular invariants are represented after reconstruction. Quantization of internal labels follows from the discrete cohomology of co-cycle classes and from transportability constraints in the physical band. Charge quantization is thereby a consequence of algebraic selection rules rather than of background geometry. Connect these ideas with standard model quantum numbers. One must classify automorphism classes and construct charge-carrying endomorphisms. In the physical band, a DHR-style program adapted to the relational typedry 1 context is the natural technical route with transferability and covariance rephrased in band language, locality and screening for internal charges are analytic consequences of finiteness conditions, such as nuclearity and the split property. When these conditions hold, one can meaningfully define approximately localized charges and study their fall-off and screening behavior in the emergent space-time.
these operator-valued representations of pre-geometric algebraic sectors. Concretely, a field is an assignment of charge and spin-carrying operators to modular charts that implements how algebraic endomorphisms are realized once spacetime is reconstructed. Transportable endomorphisms of the global algebra supply the charge sectors that fields represent, the commutation and exchange properties of emergent fields follow from modular commutators and from the braiding or co-cycle data of transported endomorphisms. Global symmetries are automorphisms that preserve modular structure across the physical band. Local gauge redundancy appears as an ambiguity in choosing transition co-cycle representatives. Gauge fields are the emergent data that parameterize such choices. Connections and holonomies in the emergent representation are encoded by non-trivial Connors co-cycles and their composition on overlaps. In this sense, what we call gauge connection is the space-time image of modular transition data. Conservation laws follow from invariance properties of modular generators under automorphisms of the physical band. These conserve modular quantities mapped to the familiar conserved currents after reconstruction. Effective field dynamics are expected to appear as compatibility of stationarity conditions on modular data and on relative entropy functionals. Classical field equations should arise as emergent consistency relations rather than as fundamental inputs. Empirical contact proceeds by identifying observables where modular origin effects could appear. Promising arenas include precision tests of locality and causality, scaling laws of entanglement entropy, and the onset of decoherence or minimal action signatures tied to the bandwidth. The modular origin of Planck's reduced constant makes the narrow bandwidth an empirical parameter. Constraints on that width translate into bounds on interference, visibility, decoherence scales, and the fidelity of semi-classical approximations in high-precision experiments. global flow.
Of a given particle species share identical mass and charge because they correspond to unitarily equivalent embeddings of the same sector. Modulo Conus co-cycles universality of particle properties is therefore a consequence of sector equivalence rather than of local field dynamics. Particle identity is not tied to space-time location. What appears as multiple identical particles corresponds to repeated quasi-local realizations of the same algebraic sector within different relational subalgebras. Generations arise when a single symmetry sector admits multiple stable embedding classes into the modular net. Each class couples differently to large-scale modular structure, producing distinct but related mass values without introducing new particles or fields. Matter and antimatter correspond to distinct DHR sectors of the automorphism structure in the presence of a physical band with a preferred modular flow orientation. These sectors need not be populated symmetrically. The intrinsic directionality associated with modular flow introduces a structural bias in how relational updates are realized, which can be inherited by the emergent space-time description in this view. Matter-antimatter imbalance is not traced to a specific bed-admittable process alone, but may reflect the asymmetries already present at the level of modular organization. Any such bias must remain compatible with CPT symmetry at the fundamental level and with the observed CP violation of the standard model, which then appears as an effective manifestation rather than the primary origin. Apparent unification of interactions at high energy is explained by the loss of resolution of relative modular phases when modular flow becomes strongly mixing distinctions between co-cycle classes. That separate interactions at low energy are no longer stable in this regime. Automorphism subgroups that act as distinct forces at ordinary energies become effectively conjugate within a larger symmetry. Unification reflects the thermal trivialization of relative modular structure rather than the emergence of new degrees of freedom. Dark matter effects need not correspond to particle sectors. Modular phase and homogeneities across networks of relational subalgebras can generate curvature without defining any transportable DHR sector. Such modular configurations gravitate because gravity reflects modular curvature, not because they excite fields. They are not localizable, not excitation-like, and not associated with symmetry representations. The distinction between particle sectors and dark modular structure is algebraically sharp. Only configurations supporting symmetry subgroup representations define fundamental particle sectors, whereas purely modular phase structures contribute to geometry without acquiring a particle interpretation. At the level of effective geometry, these contributions can be encoded in an effective stress-energy tensor, and Einstein's equations retain their formal validity. Conceptually, however, the corresponding terms do not represent matter or energy in the usual sense. General relativity implicitly assumes that all curvature is sourced by fields or particles defined on space-time. In this framework, that assumption is relaxed. Some curvature originates from the relational structure that generates space-time prior to the emergence of fields, explaining why dark matter appears gravitationally while lacking particle-like signatures. Accordingly, curvature receives contributions from three distinct sources: particle sectors corresponding to conventional matter and radiation. Large-scale background effects associated with coherent modular structure and intrinsic modular misalignment in the type 3-1 algebra, which produces curvature without corresponding to any excitation. That gravitational effects do not require DHR superselection sectors associated with localized charges does not preclude the existence of additional weakly accessible modular modes, which may contribute gravitationally while remaining non-DHR and non-particle-like. But importantly, a discovery of weakly coupled dark sectors would not exhaust the sources of gravitational curvature. Under MRF, some curvature is expected to arise from modular structure that admits no particle or coupling description at all. Pure modular curvature clusters around galaxies not through attraction or transport, but because both baryonic matter and dark curvature arise from the same underlying modular organization. Clumping reflects shared structural region rather than dynamical response. Pure modular structure does not propagate through space-time. Apparent motion arises because space-time itself is continuously reconstructed from modular relations, and persistent relational patterns are re-embedded at successive space-time locations. In the bullet cluster, the appearance of two dark components continuing along distinct trajectories reflects the persistence of two independent large-scale modular configurations. The collision disrupts baryonic stabilization but does not erase the relational identity of either configuration. So space-time reconstruction continues to associate curvature with each outgoing cluster, rather than with the shock gas. While baryonic mass is carried by particles, gravitational structure is most strongly correlated with long-lived, coherent configurations such as galaxies, which serve as stable markers of the underlying modular organization. Both particle dark matter and modular curvature contribute to gravitational effects experienced by baryonic matter. However, only particle dark matter emits mutual dianevular back reaction. Pure modular curvature influence matter through geometry, but is not itself dynamically influenced by baryonic rearrangements. Absent stabilizing anchors, modular configurations do not persist indefinitely, they reorganize. Pure modular structure is not conserved as a quantity but constrained as a pattern. Relational coherence persists only within the admissible structure of the algebra and reorganizes when those constraints are no longer satisfied. Systems with similar present-day baryonic structure but very different histories should show similar dark gravitational effects under MRF, but different ones under particle DM. If dark gravitational effects arise from constrained modular structure rather than conserved matter, then they should persist without memory, reorganize without transport, and leave no dynamical back reaction signatures, all of which are testable in principle. Vacuum energy and the cosmological constant are reinterpreted accordingly, rather than arising from summing zero-point energies of quantum fields. The observed cosmological term reflects the large-scale modular background of the physical band. This avoids the conventional overcounting problem and ties cosmic acceleration directly to the structure that
generates space-time itself. Is interpreted as the long wavelength component of the global modular background that persists when local excitations are removed. It is not a substance and not a new field, but an intrinsic feature of type the free one modular dynamics. Admissible reference states are related by Connors co-cycles, and the inner automorphism structure of the algebra supports large-scale modular behavior that dominates over local state-dependent fluctuations. When modular data are coarse-grained across the physical band, short-scale modular distortions largely cancel, while global modular features remain coherent. This produces an effective, weak, and approximately uniform contribution to emergent curvature. The resulting acceleration is smooth because reconstruction requires differentiable gluing of modular data, and uniform because the underlying modular structure is state-independent up to co-cycle equivalence. This identification is structural rather than derived. Establishing it quantitatively requires showing that a persistent modular background survives reconstruction with the observed magnitude and scaling properties, and that it maps to in fact stress energy contribution compatible with cosmological constraints.
Big Bang is an informal label for a regime in which space-time reconstruction becomes coherent. If the global reference state is done amical, the long wavelength modular mode associated with dark energy can relax over cosmological timescales. Slow drift of the infrared modular component reduces its effective amplitude in any given quasi-local reconstruction, weakening the modular contribution to emergent curvature. This weakening need not be chaotic under co-cycle stability and band coherence. It takes the form of secular drift rather than violent instability. Such reactation reflects redistribution within the physical band, rather than dissipation of modular structure itself. The richness of admissible global modular configurations permits a wide range of large-scale cosmological reconstructions within which infrared modular relaxation can naturally occur.
The hypothesis of a relaxing modular background is empirically constrained in principle. It predicts gradual, model-dependent changes in effective late-time expansion that correlate with observables probing different modular scales. Turning the idea into a quantitative test requires mapping which cosmological measures sample which modular regimes, and deriving the expected secular signatures in the expansion history, and in entanglement or entropy diagnostics. Rapid early expansion corresponds to a phase of fast reorganization of relative modular phases. Apparent inflation reflects the rapid growth of quasi-local modular coherence rather than superluminal motion through pre-existing space. In this early regime, space-time is only weakly emergent. Causal and metric notions are approximate and unstable because modular correlations have not yet settled into patterns that support persistent locality. The observed large-scale smoothness of the universe is naturally explained by early modular coherence. Relational correlations are established before fully local physics emerges, reducing sensitivity to later to quasi-local fluctuations. Singularities of classical general relativity mark the breakdown of geometric reconstruction rather than a failure of the underlying dynamics. Modular flows and Connors co-cycles remain well defined, even when no smooth manifold description can be sustained. Black hole interiors correspond to regions of extreme modular shear, where neighboring modular flows become strongly misaligned. The emergent space-time description fails locally, but the global relational structure continues to evolve without singular behavior. The structural laws and fundamental constants of emergent physics are fixed by the global type 3-1 factor and the admissibility constraints defining the physical band. MRF does not assume fundamental information conservation. Information arises only in regimes where modular contrast is sufficiently stable to support distinguishability. Ceases to exist when that contrast dissolves. General relativity possesses a local Lorentz freedom in its frame bundle that is often described as an unused symmetry. From the present perspective, the symmetry is not unused but emergent. It reflects a residual freedom inherited from a much larger symmetry, acting at the level of the modular substrate.
Local Lorentz symmetry does not originate at the space-time level. It arises as the geometric shadow of automorphisms of the global type 3-1 algebra, where modular structure is projected onto an emergent manifold. What appears in general relativity as a local frame redundancy corresponds in this framework to a small remnant of the inner automorphism group that governs relational structure prior to space-time reconstruction.
The apparent limitation of local Lorentz symmetry in encoding internal interactions is therefore not a deficiency of the underlying theory, but a consequence of truncating the symmetry spaces at the geometric level. The full internal symmetry is carried by the automorphism group of the algebra, while SO13 represents its classical imprint after reconstruction.
This clarifies why the unused symmetry of general relativity does not generate new fields by itself, yet still signals the presence of a richer underlying structure.
E equals mc squared is interpreted as the leading order expression of how a particle sector couples to the background modular flow. Mass reflects the lowest order modular misalignment of a sector relative to the physical band, and energy measures the corresponding effective modular frequency. More generally, the effective modular frequency of a sector is determined by nonlinear relative modular structure, because modular flow in a type 3-1 factor is non-factorizable and governed by Connors co-cycles. The mapping from modular data to space-time energy is not strictly linear at all. Orders, higher order modular contributions
are therefore generically present, but strongly suppressed. They do not correspond to additional fields, forces, or particle species, and they introduce no free parameters. The smallness reflects the rigidity of the modular structure rather than fine-tuning. In this sense, energy is a coarse projection of a deeper modular quantity.
The familiar relativistic energy relation captures the dominant contribution, while subleading modular structure remains effectively invisible at accessible scales.
In the emergent description, the fine structure constant is identified as the dimensionless ratio between the universal modular width, fixed by the narrow band, and the electromagnetic modular response scale governing how electric charge enters the modular relational structure.
Strong entanglement between quasi-local subalgebras can give rise to effective connectivity in the reconstructed space-time, suggesting a conceptual parallel with the ER equals EPR conjecture. In this framework, such connectivity does not correspond to pre-existing geometric bridges, but to coherent modular correlations that persist across relational distance. Dense modular configurations, including those associated with black holes, may therefore support effect and shortcut structures in the emergent geometry. This does not guarantee the existence of specific wormhole configurations, but it illustrates how entanglement and space-time connectivity arise from the same underlying modular substrate.
Magnetic monopoles can exist only if the automorphism structure of the global type free one algebra admits a DHR type sector carrying a non-trivial topological modular twist. Such a twist must define a stable modular embedding class within the physical band in order to correspond to a persistent magnetic charge. This criterion is substantially more restrictive than in conventional quantum field theory, where monopoles are introduced through field configurations on a background space-time. In this framework, the existence of magnetic charge is a global algebraic question rather than a local geometric construction. The fundamental relational structure does not exhibit global entropy production. The type free one algebra and its modular relations are stable up to co-cycle equivalence and relative modular operators. Reorganize correlations without destroying relational content. There is therefore no notion of entropy increase at the level of the full algebraic substrate.
Apparent entropy increase arises only within emergent space-time descriptions. For quasi-local subalgebras, modular flow redistributes relational information in ways that, when combined with coarse graining and restricted local access, produce the familiar thermodynamic arrow of time. This increase reflects loss of accessible information relative to a local description, not loss of relational structure itself. In this sense, irreversibility is relational rather than absolute, while local observers necessarily describe an increase of entropy. The underlying modular structure preserves the phase relations from which all physical content is reconstructed, the arrow of time. Thus coexists with global structural conservation without clear and fundamental dissipation, even though affected cosmological parameters may exhibit slow drift over long time scales. One may ask whether the physical band appears in the emergent description as the path multiplicity emphasized in the Feynman formulation. In MRF, any such multiplicity reflects structured variation of modular phases within the physical band, rather than an unrestricted sum over possibilities. Although this variation can resemble a superposition over many alternatives in the emergent description, admissibility is structural rather than probabilistic, and configurations outside the physical band are excluded rather than suppressed, while the reference structure may evolve within the physical band. The modular width of the band itself remains fixed. The universal quantum of action is therefore stable, even as large-scale modular configurations relax.
Construction program can be formulated in terms of modular information geometry. Smooth variation of modular data. Cross-relational labels allows one to extract a bilinear form from second variations of relative modular entropy. Under pseudo smoothness and finiteness conditions, this form defines a local metric structure, while half-sided modular inclusions identify causal directions. The same modular data admit an independent spectral characterization. Modular Hamiltonians associated with quasi-local subalgebras can be used to define local spectral generators whose induced distances provide an internal consistency check on the entropically defined geometry. Agreement between these two constructions stabilizes the reconstruction, fixes residual normalization. These entropic and spectral perspectives are not alternative routes, but complementary aspects of a single modular reconstruction pipeline. Establishing their equivalence and global consistency requires proving modular smoothness, nuclearity, and split properties for the relevant relational inclusions. Whether these conditions suffice to guarantee a unique smooth Lorentzian space-time remains an open mathematical problem. Formalizing MRF requires identifying structural conditions under which modular data emit a geometric interpretation. These include modular covariance across overlaps, the existence of calibration patches that fix modular time normalization, sufficient half-sided modular inclusions to generate causal directions, smooth dependence, smooth alert generators on relational labels, and finiteness conditions such as nuclearity and the split property to control local information. 10. When these conditions hold within the physical band, modular flows, relatives, modular operators, and Conisco cycles can be organized into a coherent relational structure. Metric and causal data arise simultaneously from controlled variations of modular phases rather than being posed independently. Space-time geometry is reconstructed as a consistency structure of modular relations rather than as a background arena. Establishing the existence, uniqueness, and global consistency of such reconstructions remains an open mathematical problem. The present framework isolates a modular hypothesis that must be analyzed and clarifies which aspects of space-time geometry are expected to follow from them. In this sense, MRF provides a precise research program rather than a complete construction. Several key mathematical questions remain open within this framework. Establishing Lieb-Robinson type bounds or suitable generalizations for modular flows of relational subalgebras and type 3-1 factors would place the emergence of a finite invariant causal speed. Related tasks include proving stability and smoothness, properties of modular Hamiltonians across admissible families, characterizing co-cycle rigidity at large scales, and determining precise conditions under which modular curvature reproduces Einstein dynamics. These problems are mathematically well posed and independent of interpretational choices, and they define a concrete research program at the interface of operator algebras, modular theory, and Mercury geometry. The reconstruction strategy implicit in this framework naturally lies in second-order differential geometry, relative modular entropy, and Fisher information. Define quadratic forms on infinitesimal relational variations, and these second variations supply the metric data from which geometry is reconstructed. Once relative entropy is taken as primitive, first-order geometry is insufficient, since the relevant structures are determined by second derivatives rather than by linear displacement alone. Second-order geometry also provides a natural setting for combining modular drift. The reducible modular fuzziness, modular Hamiltonians generate deterministic relational flow, while the absence of exact factorization in a type 3-1 algebra introduces intrinsic phase dispersion. Stochastic or diffusion-like terms therefore arise structurally rather than probabilistically. Brownian principles formulated at second order accommodate both features simultaneously and yield dynamics governed by second order differential operators, precisely the class of operators associated with modular generators. From this perspective, modular operators play a dual role. They generate relational time flow and simultaneously control stability, dispersion, and curvature through the second order structure. The resulting dynamics resembles thermodynamic or entropic approaches to gravity, but without appeal to coarse-grained horizons or ensemble reverging geometry. And its dynamics emerge from individual modular relations, and their evolution reflects the second-order structure inherent in the relational substrate itself.